Bardus is a data-focused, solution-oriented consulting firm that leverages best-of-breed tools to deliver rapid business value. My name is Daniel Parton. I'm the lead data scientist at Bardus. I'm going to present a demo app we built in ClickSense, which features a data science technique known as association rule learning. The app is up on our demos website. It's the medical comorbidity analysis app shown here. Association rule learning is basically a technique that aims at finding common associations between items. The classic application is for finding products commonly purchased together in a supermarket, known as market basket analysis. However, in this demo we'll be looking at a medical dataset containing patient diagnoses, and the aim is to find diseases which are commonly found together in the same patient. The medical jargon for this is comorbidity. So first let's take a look at the data. We have data here for 267,000 patients, all anonymized of course, and there are about 1 million historical diagnoses recorded for these patients. The diagnoses are split into a disease category and a disease name. There are 17 different disease categories and 15,000 different diseases in this dataset. Now let's take a look at the results of the association rule learning. And just to point out that for this demo app, we carried out the analysis in Python with an open source library for association rule learning named Orange, and we then loaded the results back into ClickSense. However, I'll be discussing other more integrated solutions later. So this table shows the list of associations produced by the analysis. Note that we're looking at associations between disease categories in this case. You can see that this association is between diseases of the digestive system and diseases of the blood and blood-forming organs. Each association can be described with a number of metrics which come from the association rule learning, including support and lift. The lift is basically the strength of the association, or more specifically, it describes how much more likely an association appears to be in the data compared to if all associations were equal and random. So this association is 2.53 times more likely to occur than if all associations were just random. And we'll come back to the support metric later. This rather cool looking visualization is known as a chord diagram. The idea here is that the thickness of each chord represents the lift. So for example, we can see that some disease categories are associated with many other disease categories, such as mental, behavioral, and neurodevelopmental disorders, while other categories are more isolated. So now, rather than looking at associations between the broad disease categories, let's dive in deeper and look at associations between actual diseases, because this is where we start to see some really interesting insights. You can immediately see we have a lot more associations to look at, and we may need to do something to make this data easier to sift through. This is where the support metric comes in. I'm going to set a minimum threshold for support, let's say around here. So now we are only viewing associations with a support of at least 620, meaning that the disease in the first column appears at least 620 times in the dataset. This means we have a much more reasonable amount of data to sift through when we're looking for interesting associations. The chord diagram looks a lot easier to read now, and again we can see some diseases with a lot of associations, such as GERD down here, and also vitamin D deficiency. Whereas insomnia up here has relatively few associations, but quite strong ones, since some of these chords are relatively thick. You can see one of the thickest chords is this one, which represents an association between vitamin D deficiency and malnutrition following gastrointestinal surgery. You can see this in the table as well, which is sorted by lift, that this is actually the highest lift. And having done a little research into this, I found a medical research paper which shows that it's a known problem whereby certain gastrointestinal diseases can result in vitamin D deficiency. If we scroll down a bit in the table, we see here a link between anxiety and insomnia. I'm sure you could imagine that anxiety could be a cause of insomnia or vice versa. Below that, we see a strong link between tobacco abuse and COPD, a type of lung disease. Obviously, today the link between tobacco abuse and lung disease is well known, but it at least helps validate our analysis that this comes up as one of the stronger associations. If we scroll down a bit more, we see vitamin D deficiency pop up again, this time in association with osteoporosis. Again, I did a bit of Googling and found a scientific paper showing that vitamin D deficiency is a known risk factor for osteoporosis. So you can see how, looking through the results of this analysis, you can start to build up a picture of which diseases are typically associated with each other. Finally, I wanted to talk about the technical details of how this analysis was integrated with Click. For this app, we did the analysis in Python and loaded the results into Click. However, it would certainly be possible to integrate this kind of analysis directly into Click by developing a custom extension, which is something we have often done at Bardes. Additionally, we have another demo app on cloudera.click.com called Market Basket Analysis, which applies association rule learning to a much larger dataset and uses the big data processing tool Spark to do that. By running both Click and Spark on top of a big data framework provided by Cloudera, it is easy to integrate these different tools and productionize complex analysis tasks. If your business has any applications which could benefit from association rule learning, or even if you think they might benefit but are not quite sure and would like to discuss with us, please feel free to get in touch and we'd love to brainstorm some ideas with you.